This video focuses on analyzing a problem that involves applications of two concepts in kinetic molecular theory. These are average translational kinetic energy and root mean square speed of an ideal gas molecule. So just hang on, stick around, watch and learn. The question is, for the first 380,000 years after the Big Bang, the temperature of the matter in the universe was too high for nuclei and electrons to form atoms. The first hydrogen atoms, mass per atom 1.67 times 10 to the negative 27 kilogram, did not form until the temperature had dropped to about 3000 Kelvin. Question letter A. What was the average translational kinetic energy of hydrogen atoms when the temperature was 3.0 times 10 to the third Kelvin? And question letter B. What was the RMS speed of these atoms? To answer question letter A, we need this equation. Ke sub TAV means the average translational kinetic energy of the particle, in this case, hydrogen atoms. So it is equal to 3 halves multiplied by a constant K multiplied by the absolute temperature capital T. The value of K is equal to 1.380649 raised to the negative 23 joules per molecule Kelvin. And this constant is referred to as the Boltzmann constant. Now, based on this equation for average translational kinetic energy of molecules or atoms, we say that the average translational kinetic energy of any particle, whether it is a molecule or an atom, like in this case, we're talking about hydrogen atoms, okay? It depends only on absolute temperature, capital T, and not on variables like pressure, volume, mass, or the kind of particles. So, to continue answering letter A, we substitute the given to this equation. We have 3 halves multiplied by Boltzmann's constant. We only use 4 significant figures for the constant K. So 1.381 raised to the negative 23 joules per molecule Kelvin and multiplied by the absolute temperature 3.0 raised to the third power Kelvin. So simplifying, we will get the value 6.2 raised to the negative 20 joules. Alright, so this is the average translational kinetic energy of a hydrogen atom. For question letter B, we use the formula for the RMS speed V. Okay, the formula is V RMS is equal to the square root of 3 multiplied by Boltzmann's constant K and the absolute temperature capital T divided by the mass of the particle small m. So, unlike the average translational kinetic energy, okay, the RMS speed of a molecule or an atom depends on the mass of the particle or atom. Right? The smaller the atomic mass, the faster is the speed of a particle. And so, for a hydrogen atom in this problem, okay, we can calculate for the RMS speed again using this formula. So we substitute square root of 3 multiplied by Boltzmann's constant and the absolute temperature divided by the given atomic mass of the hydrogen atom, which is 1.67 times 10 to the negative 27 kilogram. So doing your math, we will get this root mean square value of the speed equal to 8.6 raised to the third power meters per second. Now, this relatively high speed of hydrogen atoms or molecules explains why there's little hydrogen in the Earth's atmosphere compared to, let's say, nitrogen or oxygen gases. Hydrogen particle RMS speed is greater than the Earth's escape velocity. So, hydrogen gases can easily escape into the outer space. And before we end, let's take a look at the key concept that we have applied in this problem. The average translational kinetic energy of a molecule in an ideal gas at absolute temperature capital T is expressed as 3/2 times Boltzmann's constant K and the absolute temperature capital T. Alright? No matter what the mass of the molecules is. Right? However, the root mean square speed or VRMS of molecules, that is, the square root of the average value of V squared in an ideal gas, alright, depends on the mass per molecule as given in this equation for the root mean square speed, that is equal to square root of 3 multiplied by Boltzmann's constant and the absolute temperature divided by the mass of the molecule. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.